Let's talk about why the Asian giant's greatest military asset could become an easy target the moment it decides to make a sharp turn in mid-air. Forget the propaganda about the invincibility of fifth-generation platforms. The fundamental reason this starfighter faces serious doubts among experts isn't a flaw in its weaponry, but an insurmountable geometric compromise in its fuselage and a long-standing engine crisis that turns its rear end into a giant torch in the face of enemy heat signatures. The so-called mighty dragon of Chinese aviation is considered the crown jewel of its nation's military power and its main contender for air superiority over the Pacific Ocean. However, when the design decisions are analyzed through the lens of aeronautical physics, engineers and military intelligence analysts agree that the aircraft suffers from serious structural flaws. This isn't to call it a bad platform, as it is fast and boasts advanced technology, but rather to understand that all military engineering involves unavoidable compromises. And in this case, stealth was sacrificed in favor of agility. If you're passionate about unfiltered military aviation, the physics of stealth technology, and strategic analysis of the world's most advanced fighter jets, subscribe to the channel and turn on notifications so you don't miss any episodes. The most distinctive visual feature of this aircraft is the presence of movable forward fins mounted just ahead of the main wings. While these fins grant it formidable maneuverability at low and medium speeds, they represent a critical vulnerability to its stealth capabilities against enemy radar waves. For an aircraft to be truly invisible, its outer surfaces must maintain continuous angles that deflect electromagnetic signals away from the enemy's receivers. When an aircraft performs evasive maneuvers or mid-flight adjustments to correct its trajectory, the forward ailerons constantly rotate and change position. This rotation immediately disrupts the fuselage's continuity, creating reflective edges that act as metallic flashes on the enemy radar screen. The instant the ailerons move to initiate a turn in close combat, the aircraft's discrete shape vanishes completely. This weakness in moving surfaces is compounded by the problem of the electromagnetic signature from the sides. While the aircraft's nose is reasonably optimized to scatter radar waves from the front, the angles of the forward ailerons project a massive radar echo when the aircraft is viewed from the sides, above, or below. Rival fifth-generation interceptor fighters, such as the most advanced American platforms, could detect the Chinese aircraft at massive ranges as soon as it banks its wings and ceases to fly directly toward the target. Adding to the geometric limitations of the front wings is the long-standing and major headache for the Chinese aerospace industry: the production of high-performance military turbines. For decades, Chinese engineers faced severe challenges in manufacturing metal alloys and ceramic coatings capable of withstanding the colossal pressures and extreme temperatures generated inside fifth-generation engines. This technical deficiency meant that most of the operational fleet initially flew powered by Russian-made turbines or early locally developed reduced-capacity versions. This reliance on older generation engines denies the fighter-bomber the ability to fly in true supercruise, that is, the ability to sustain supersonic speeds for extended periods without burning additional fuel. To break the sound barrier and accelerate in an air combat situation, the aircraft is forced to engage afterburners. This mechanism injects fuel directly into the exhaust to multiply thrust, but it generates two catastrophic consequences for the aircraft's survivability in flight. The first consequence of afterburner ignition is the creation of a gigantic plume of heat at the rear of the aircraft. The massive gases expelled at thousands of degrees Celsius transforms the aircraft into a brilliant infrared torch in the atmosphere. Optical and thermal sensors integrated into rival fighters, as well as the infrared guidance heads of the most modern air-to-air missiles, can lock onto the aircraft's heat signature at astronomical distances, completely negating any tactical advantage provided by the radar-absorbing paint on the front. The second major weakness related to propulsion lies in the shape of the exhaust nozzles themselves. While American fifth-generation fighters use flat, integrated nozzles to cool the exhaust gases and deflect radar waves with serrated edges, the Chinese aircraft has mostly flown with unobstructed conventional circular nozzles. These traditional round openings not only fail to dissipate engine heat but also reflect radar waves from the rear of the formation with a massive echo. Although the Chinese military industry is testing and gradually installing a new, more powerful engine designed to address the lack of thrust and improve integration, The large thermal mass and rear electromagnetic exposure remain a significant vulnerability in the existing fleet. In a direct engagement where aircraft must maneuver and escape after launching their weapons, the exposed rear of the aircraft represents an extremely vulnerable target that opposing fighters will be able to exploit from a safe distance. Beyond the geometry of the fuselage and the thermal signature of the engines, 21st-century air battles are not decided solely by the aircraft's agility, but by the speed and precision with which its computers process environmental information. A modern fifth-generation fighter bomber must function like a flying supercomputer capable of collecting data from electronically scanned radars, optical sensors, and satellite links, synthesizing all that information to present it to the pilot clearly and instantaneously. Although the Asian Giants Air Force has managed to integrate advanced, state-of-the-art radars and high-resolution optical sights into the aircraft's nose, the Eastern military industry has faced colossal challenges in optimizing software algorithms under intense electronic jamming scenarios. In a real theater of operations over the ocean, the airspace will be flooded with jamming signals, false electromagnetic echoes, and digital noise designed by enemy powers to blind the sensors of attacking aircraft. If the aircraft's onboard computer programs fail to effectively filter out the overwhelming electromagnetic noise, the pilot immediately loses the advantage of situational awareness. In an environment saturated with electronic warfare, a failure in data fusion means the computers will be unable to distinguish between a real threat, a digital decoy, or an allied aircraft. This temporary blindness leaves the crew vulnerable to being caught off guard by projectiles launched from beyond visual range before the cockpit display can register the attack's origin. Long-range combat capability depends on the primary sensor maintaining lock onto the target without revealing the aircraft's position. However, when an aircraft is forced to increase its radar output to overcome enemy jamming, it acts like a beacon in the night. Passive radar antennas on rival fighters can track this radar output with pinpoint accuracy, allowing the adversary to launch long-range missiles without having activated their own active radars to avoid detection. This weakness in software processing under cyber stress turns beyond visual range combat into a strategic game of Russian roulette. While Western platforms have accumulated decades of practical experience refining their data analysis programs in real-world exercises with allies around the globe, Eastern aviation has yet to demonstrate the operational maturity of its internal code in a full-scale electronic warfare scenario, where a 1-second delay on the cockpit display means the aircraft's destruction in mid-flight. Faced with mounting evidence of these vulnerabilities, the Chinese Air Force has launched an ambitious modernization program to address the most glaring shortcomings of its flagship aircraft. The Asian aerospace industry's primary focus is the mass production of a new version of its domestically developed high-thrust engines. This upgrade aims to provide the necessary power to sustain supersonic speeds without relying on afterburners, significantly reducing the telltale heat signature at the rear of the aircraft. In parallel, modifications are being implemented in the engine exhaust outlets, testing toothed covers and ceramic matrix coatings designed to cool the outgoing gases and dampen radar reflections. However, even if the new engine manages to improve propulsion performance and mask some of the emitted heat, there is an insurmountable geometric dilemma that the aircraft will have to contend with throughout its service life: the presence of the movable forward wings on the nose. The physics of aerodynamics and electromagnetic transmission is categorical and inflexible. No matter how much progress is made in the composition of radar-absorbing paints or in onboard computer algorithms, the physical rotation of the forward fins during tight turns will continue to disrupt the fuselage's continuity in flight. It was precisely to avoid this design flaw in stealth capabilities that the designers of the most influential fifth-generation fighters in the West opted to discard the use of movable forward fins, preferring to adapt canted tail fins and thrust vectoring engines. This reality demonstrates that the Chinese Air Force's flagship fighter bomber is not a defective machine, but rather the result of a deliberate strategic compromise. Its creators prioritized acceleration, intercontinental range, and low-altitude maneuverability over absolute stealth from all angles. In a real combat scenario against adversary fighters equipped with state-of-the-art thermal sensors and extended-range radars, this design choice exposes the aircraft to catastrophic losses during the approach phase or the moment it attempts to break contact. The rigorous and dispassionate analysis of the most advanced military platforms on the planet constantly reminds us that, in the stark reality of modern warfare, there are simply no invincible machines in the air. Every aircraft design is, in essence, a delicate and complex balancing act of technical trade-offs, prioritizing certain critical attributes at the expense of others. Therefore, true tactical advantage in future conflicts will not lie in the absolute perfection of a single weapons system, but rather in the comprehensive ability of nations to master the laws of aeronautical physics, ensure the unshakable maturity of combat software against electronic warfare, and enhance the skill of pilots to accurately identify and exploit the adversary's vulnerabilities while shielding their own structural weaknesses. Ultimately, a deep understanding of the real limits and inevitable contradictions of military engineering is the first, critical, and necessary step in deciphering the complex and shifting balance of power that will be contested in the skies in the coming decades. If you've been captivated by discovering the unfiltered truth and the physics behind China's most advanced fighter jet, subscribe to the channel immediately, like this content, and share it with your aviation enthusiast friends to continue exploring the secrets of modern warfare together.